Hi, and we continue with this year's Technology Days with our next presenter, Kevin Neal. Let me just bring you to the stage, Kevin. Right, okay, I can see you. Can you hear me okay?
Yep, can hear you just fine.
Okay, that's excellent. That's always the first test. We can see and we can hear you, so that's good. Right, so this is looking at for we've heard earlier about dependability and FRACAS systems for failure reporting, analysis and corrective action. So here we've got an example where this has been deployed within the US Navy, and it's an example of how that's been implemented and what the benefits are. So I'm going to bring you to the stage, Kevin. I'm going to bring your presentation on. So is that all okay? Can you see that okay?
Yeah, looks good.
And you've got control. I'll see if we get some questions from the audience, and we'll do some Q&A at the end. But okay, off you go. Go ahead, Kevin. Thank you.
Very good. Thanks, Rob. As Rob said, this is an implementation of the XFRACAS tool set at a customer called NAWCAD, and I'll describe that here in a second. But just as a little bit of an introduction to myself, I'm the technical leader or solution architect for this particular application. So I've got a lot of the background associated with why we did what we did and how we did it. So of course, if you have any questions, I'll do my best to answer them. So let's jump into the presentation. So to start with, just a brief background on what NAWCAD is. It's really the Naval Air Warfare Center aircraft division for the US Navy. And what they're responsible for is basically anything that flies in the US Navy. That could be fixed wing aircraft like the F-18 and the F-35, rotor aircraft, various helicopter programs that are taken up in the US Navy. But increasingly, it's unmanned aerial systems, drones, and the systems that support them. But it's also things that sit on wing, like weapon systems, jamming systems, that sort of thing that sit on the wings of aircraft, as well as all the support equipment. That could be the catapults and arresting gear on an aircraft carrier. It could be the landing systems or the radar systems associated with managing aircraft and flights on aircraft. So really a very broad set of equipment that they're responsible for. Now, the biggest thing in the US Navy is readiness, the ability to perform the missions that's expected at the moment that they need to be performed. And so readiness of equipment and its ability to perform those flights and those missions is paramount to the US Navy requirement. And they have a lot of challenges with this. You may read about it in the news, about readiness of various pieces of equipment and the ability to keep things flying. It's a big problem. It's a big challenge for them. And one of the things that they identified that was truly problematic was the fact that they had a various mixed bag set of tools that they were using to track and improve readiness across all these different pieces of equipment. So whereby they may have a great system in place for the F-18 that's been in operation for over 30 years, they had other systems where they had nothing at all, where people were basically putting things together on spreadsheets and running them that way. And one of their goals was to create a common system to be used across all their different programs. And so that started about 5 years ago that they made that decision that they wanted to do that work. We got involved 4 years ago and have been working to build this program ever since. And so the key to what they're trying to do is actually create this common system that can be used across all the various platforms, of which there's about 30 of them. And what they wanted to be able to do is to provide a common system to basically do all the work that they wanted to do to understand readiness, understand the capability of their equipment, and to actually perform the corrective actions necessary to improve the overall readiness of the system. Now, just taking a step back again for a second, this had to basically work for systems that have been in operation for 30 years, so what we call in sustainment. It had to work for new programs that were just under development. It had to work across multiple OEMs, and it had to account for all the various nuances associated with each program. So although it's a common tool, it had to be flexible enough in order to accommodate all those different needs. The other thing that they said right from the outset is it had to be based on COTS software. And so they came to HBK and the XFRACAS platform that we have to use as the basis for this entire system. Now I'm just going to jump to the punchline at the outset here to explain what we've been able to accomplish over the last 4 years. And of those 30 or so programs or platforms of various pieces of equipment that fly within the U.S. Navy, we've implemented 20 of those platforms to date. We're tracking over 4 million maintenance actions per year. So we have systems with probably 60 or 70 million maintenance actions in them already. And we're tracking 1 million flights per year. So it's a very large system with a lot of maintenance, a lot of information coming into it. We've already demonstrated as part of this program and working within what's called the RCB process, which is the Reliability Control Board process, of which the XFRACAS tool is a part of that. We've already been able to demonstrate a 20% increase in operational readiness. That's huge. That's a big jump in improvement in overall readiness of the various pieces of equipment. But it's just the starting point. You know, that's probably the low-hanging fruit, and then we want to go further. So a lot of what we do in the program continuously is to try and add new capabilities and new features, which will allow us to assess and improve the overall readiness of the fleet. We've also been able to eliminate a lot of the processing backlogs that occur. And this was a big reason why readiness wasn't being covered up to this point, is that it just took real time to take all of this maintenance data, process it, understand it, and identify real issues and perform those corrections. A lot of what we've done within the XFRACAS tool is to actually be able to improve that overall processing time. So let's jump in and look at the system itself and how it works and what it does. This particular graphic identifies the two key pillars of the XFRACAS system. So you'll see there on the right-hand side, what's called R&M is reliability and maintainability. That's the process of basically looking at maintenance actions, understanding whether there's key degraders that need to be investigated and allow us to work through those and make those improvements. So that's that right hand. And for most of you that have worked in a FRACAS system or worked in reliability, that'll be a very familiar pillar in this overall system. On the left-hand side, you have the HM work, which is health monitoring. This is where we're bringing in diagnostic data that comes to us from the flights themselves. These are the flight computers and mission computers on board the aircraft. And if they identify any kind of diagnostic issue, we pull that information in as well into the XFRACAS system. And I'll have to say that putting these two pillars together is probably the key benefit offered by XFRACAS over some of the systems that they were using to date. The fact that we're looking not only at the maintenance data, but the diagnostic data side by side in a single system allows us to do a number of different things that they simply couldn't do before. And really, it's related to understanding how the health monitoring data is actually providing benefit or establishing its effectiveness to understand what maintenance should be performed, but as well to assess when maintenance is performed, whether that maintenance itself has been effective. So putting those two things together in the same system is a big benefit to the overall system. So what I'm going to do is I'm going to take this picture apart and kind of walk through it from the top down and show you the different elements of the system, how it's used within NAWCAD, so that you've got a sense of the overall nature of the system and what we put together. So like I said, we're going to start at the top at the box called SDR, which stands for Standard Data Repository. And a big element of putting the system together was actually to collate the data into a single repository, a single data lake where we could actually pull that information effectively. As you can imagine, in the Navy, data is collected in the field through a number of different systems. They have a maintenance system for aircraft specifically. They also have a separate maintenance system for maritime or ship side use, and we have to pull that information together, get it into a common format. We also have to pull in all that health monitoring data, all the diagnostic data that comes off the flight and mission computers, which are completely different for each platform that we work with. We have to be able to parse that, turn that into something that's readable and consistent, and bring that into our system so that we can use it in a common way. And the standard data repository allows us to do it. It's a Cloudera system. If you're familiar with cloud-based systems, it's based on Cloudera. It's managed by NAWCAD, and they've given us access to basically collate and collect this data together and put it in a common format. We also use that repository to pass data back. So any updates or corrections that we make to the data inside the system, we pass that back and publish it into the standard data repository. So we're a good corporate citizen within NAWCAD to make data available for other teams to use. And again, this is a big part of improving the overall readiness of the system. It's not just for the reliability engineers, it's for the logistics people, it's for the PLM people, it's for the RCM people, all the different groups of users that may take advantage of this quality data that's been put together in XFRACAS. We make available and push back to them. Okay, let's progress down the R&M arm of this overall system. And we're going to start with the first three boxes, basically what we're doing when we bring that data in from SDR. And the most important thing for the engineers to start with is to create that high quality data. So reviewing and validating of that maintenance data is truly a key activity to what they're trying to do. Now, how much of this review and validation they do depends on the program that they're in. If they're a program that's been in sustainment for 30 years and they're running 1,000 different aircraft, chances are they don't have a lot of time to do this work manually. They don't have a large group of people to do this kind of overall work. What in those cases, what they're focused on is key degraders. Hey, there's a problem part. Let's analyze it in some detail and use a fairly established or sophisticated process to look through that data. For those programs, they'll primarily count on our auto processing, the work that's being done by XFRACAS to validate the data coming in, to score it, and we're going to talk a little bit about that, and all of that work. That's basically what they would count on. Now, if I go to the other extreme and look at a brand new program, maybe one that's in test evaluation or even before that, they'll look at every single maintenance action in detail. And they'll involve the OEM in that work. They'll make sure that the data is absolutely correct. They understand exactly what was done, why it was done. They'll review it, and then they'll actually put it through an audited review board process, what's called an RMRB. So you've got some PMAs that are going to that extent to understand what's happening inside the system. So again, the XFRACAS tool, it needs to cover all those different scenarios, all the way from sustainment all the way back to test and evaluation. And that's basically what we're looking at. So what's in a maintenance action? The maintenance action itself, I've listed a number of the key properties that are associated with the maintenance action. Things like establishing the aircraft and the part number, where the work is being done, what was the original issue, called the discrepancy, and the corrective action, what action was taken, and why was it taken. And then they spend a lot of time categorizing the maintenance action, what's called reason codes, action taken codes, malfunction code, what was actually broken. And really important in an aircraft industry is when it was discovered. Was it discovered in flight? Was it discovered in a ground test? Was it discovered during maintenance? It's really important to them to understand those kind of characteristics. Of course, if they removed a part or installed a part, they want to keep track of the part number and serial number. And they want to establish some key elements that I've listed down there, highlighted. The mission impact, what impact did it have on the overall mission, which relates back to our readiness. The maintenance time, how long did it take to do the work, the elapsed time, and the maintenance effort that was actually performed. And the final thing on that list, really at the bottom there, is the score, and that's the relevancy. Whether it's a reliability relevant MAF, meaning that a part was failed or broken and needed to be replaced, whether it was maintainability relevant, meaning that it simply needed to be fixed or adjusted or maintained in some way, or not relevant at all, meaning it was just part of a general inspection, maybe that there wasn't any real work that needed to be done. Scoring it that way is kind of the essence of what they're trying to do when they say they score a maintenance action. They're also interested in tracking the flight and what flight was associated with this particular maintenance action. And we're going to see why that's important a little bit later. So in terms of our auto processing, we perform a number of steps, and I just highlighted 3 of sort of the key ones here. The first one being that scoring process. This one's really important to us because of the number of maintenance actions we collect. As I mentioned, there's around 4 million per year. Mostly they're going to be interested in the reliability relevant maintenance actions. So we have an auto scoring process that we use to establish which of those maintenance actions are reliability relevant. And that process it's an explicit algorithm. It's about 95% accurate to isolate and identify which are reliability relevant. That gets us from that 4 million maintenance actions a year to around 10% of that, about 400,000 per year. And that's really what they're focused on. Now, another aspect of what they do is what I call a parent-child relationship. The way that the U.S. Navy performs their maintenance actions, they basically take any part that's replaced or repaired, and they create a separate maintenance action for it. So any part that is a repairable part gets its own maintenance action. Well, it might be the case that a lot of those maintenance actions are performed in support of the actual maintenance actions, which is problematic. Say, for example, you have an engine, and let's say your fuel nozzle's burned out. You need to replace your fuel nozzle. Well, you might have to remove the cowling. You might have to remove various sections of the engine to actually get to that fuel nozzle to repair it. They would create a maintenance action for each one of those steps. So for removing the cowling, for taking apart the combustor can to get inside, get to that nozzle, making the replacement, each one would be its own maintenance action. So what we do is we look at those maintenance actions and we group them together, and we say, let's identify what is the true nature of the problem. In this case, the fuel nozzle, and we make all the other maintenance actions children of that parent. And why that's important is because it sets the count of what was actually the true problem in the maintenance step. It identifies what that true problem is and sets it as the parent, and then it relates all the associated maintenance time and maintenance effort to that parent. And that represents probably about 30% of the maintenance that goes on. It's trying to create that relationship. So that's really important to us to make sure that we get accurate counts of what truly is problematic. And the other thing that goes on in the auto processing is that flight association, really to identify which flight is associated with that particular maintenance action. Okay, so we do all that pre-processing work, and then we scrub and score it, and that's usually performed by an analyst. So someone's job is to basically look through that data and understand what's there. And in a lot of cases, what they're trying to do is they're trying to establish what the failure mode is, because that's not recorded by the maintainer in the field. They're trying to establish what that failure mode is, and they're trying to make sure that they agree with the relevancy of that particular maintenance action as scored by our system. And so they'll have a chance to look at that and review and approve it. Now, this is something that I'm going to say that that NAWCAD is not really that good at yet. This idea of actually setting the failure modes. Some of the programs better than others, but that's a real big opportunity for us going forward, is to accurately set it. And maybe part of the reason was because they didn't have a common FRACAS tool before to be able to use, and they weren't really focused on getting the failure modes right. But we basically put the tools in place to make that possible. And so I think going forward, and I have a slide at the end where we talk about this, that's going to be a big element of where we can help them improve going forward. Okay, some of the other things that they check in terms of the data coming in, is all the classification codes, making sure they're correct. I can regale you with stories of when those get incorrectly set and what they do. And a big part of XFRACAS is being able to correct those en masse. So if they have a systemic problem with classification codes being set incorrectly on the mass, they can correct those very easily within XFRACAS. So it's a big part of really helping them get their job done more quickly. Finally, if a particular program is applying this process, this RMRB process, the official review of the maintenance actions, as I mentioned earlier, that's primarily when you're in early test evaluation and working directly with the OEMs. But even some of the programs in sustainment continue to do this. They'll actually sit down with all the maintenance actions for a particular period of time, particular squadron, and they'll set up one of these RMRB reviews. They'll invite participants to look through the data, make sure they agree with how it's been scored, how it's been corrected, collect any comments, identify any underlying degrader issues, and then formally review that and make recommendations going forward. So that review process is also part of the XFRACAS system, and it becomes an auditable official trail for the work being done. Now, I did talk a little bit about the failure analysis that was in there and the job that's being done. One of the things that NAWCAD has done for failure analysis is actually to send parts out to the OEM to have them review and understand what those failure modes are. And they'll get that back in the form of a spreadsheet, maybe once a month, once a quarter. Here's all the parts that you sent to us. Here's all the reasons that they failed. And we made it easy in XFRACAS to import that data back into the system. And so basically, we take the failure analysis that's given to us by the OEM, probably has a part number and a serial number on it. May actually have a job code, but not very often. But it identifies the failure mode and the failure analysis. When we bring that in, we then look to match it with the maintenance action that was associated with sending it out to the OEM. And we then can apply that particular failure mode and failure analysis to that maintenance action. Well, underlying that maintenance action is a responsible part. This was the part that was associated with that maintenance action. We can then tie that failure mode back to that part. And so we can start to build up the library of failure modes in the system by using this vendor failure analysis. So that's a way of sort of implementing or automating this process of getting the failure data in there. Okay, so that's the R&M side, and basically what we're doing to try and control things. Now let's take a look at the HM side and what we're trying to do over there. And we follow a very similar scoring type process for HM data, which involves auto processing, an analyst review of that data, and then what's called a BRB or bit review board process that can actually review and approve that data going through the system. So just to give you some context, when you fly a flight and get back this data, you can get thousands of these alerts in the data. So on any individual flight, from the mission and the flight computers, there can be thousands of these alerts. And what we're trying to do in our auto processing is identify specifically those particular alerts we're interested in. Those are the ones that are interesting. Those are the ones that are related to maintenance. And so a lot of what we do is take that thousands of alerts and reduce it down to the handful that are truly important to us. And we do this with what's called a fault isolation detection code, or a FID code. And that FID code, if I show you some examples of it, maybe it helps explain what a FID code is. The FID code scores that particular alert in terms of its ability to detect and isolate a fault. So when I get an alert in the system and it says, okay, it's this particular alert on this particular subsystem, can I isolate that to a particular set of parts that could be problematic or broken? And does it detect and identify the true issue? In other words, does it help the maintainer understand what they need to go fix? And so what we do is we actually will score each one of these codes coming in based on our known or expected sense of whether that particular code is able to isolate or not. And this is an ongoing process to upgrade and improve the quality of these of this analysis by looking at the data itself. And so if we get a particular alert, we look at the maintenance action, we'll try and understand, did it isolate it? Did it detect it correctly? And then we'll update the scoring on these particular alerts. But these are some of the alerts that are there, or what we're trying to do in the system. So we're trying to identify those codes where we correctly detect and isolate, like the first code there, the A113 code. In that particular case, you would apply that code if you could isolate it down to 3 parts, as opposed to 1 part or 2 parts. Can you isolate it down to 3 key parts? And you would score it that way. If you look down the list there, you'll see a false alarm, the F110. That's an example where we didn't have a failure. That's where an alert occurred. We did the maintenance and we found that there was really no problem. And so it was just an alarm that wasn't meaningful to us. Those are important, because we don't want false alarms, but this is the way we actually score it through the process. So this gives an idea of the kinds of things that we do. We're identifying how we detect and isolate issues, and also some of the actions that we take associated with them. And we kind of bury those into the FID codes. Okay, so in terms of our processing, every single flight that comes in to the system that actually employs this process, we basically look at every single alert that's there. First of all, we identify the mode that the aircraft is in, whether it's in a power up or power down sequence, whether it's in a pre-flight mode, whether it's in an in-flight mode. We can gather this from the data that they provide. And this is important to us because they'll take whole swaths of these codes and say, hey, we're in the power up phase. We don't trust those codes. We're not interested in them. We're just going to mark them as codes that we're not looking at, not ones that we're going to focus on. Primarily what they're going to look at is the things that are in pre-flight, in-flight, and post-flight. And they'll basically then run through and will perform the auto processing and set the FID codes associated with each of the other systems. And like I say, that will help us identify where we've isolated an issue, where we have false alarms, whether we have known issues in the codes that are there, that kind of thing. We can do all that with this pre-processing. Now, to help us do this, we built a processing rules engine, which allows the users to basically say, here's the subsystem and the alert code that we have. This is how we score it. By known experience or whatever, this is how we would score it. And we put together these processing rules to basically look through that data and help understand what's there. We do it in a way that tries as best as possible to replicate the kinds of alert scenarios that come up in the flight. Some of those scenarios are quite simple. Here's a subsystem, here's an alert code, it's in flight, boom, here's the code that you should apply to it. But some of them are more complicated. We get what's called cascading alerts. So you get a main bus power failure, and you get a series or a sequence of other alerts that occur as a result of that power failure. You really only want to score the power failure as the problem and the other ones associated with it. And we're able to do that. We're able to create those cascading styles of alerts within the system. We can also handle things like reoccurring alerts. This is the case where you may get an enunciation on your panel. As a pilot, you acknowledge it, you get it again, you acknowledge it. The simple action of getting an enunciation and an acknowledgement may not trigger an alert, but if it happens enough times, we say, hey, joke's over, there's a real problem here, we need to track this down. We're able to accommodate that in what we call reoccurring alerts as well. So a number of different scenarios that we apply in order to establish how to do that scoring. Then we provide that information to the analyst. And the analyst can then take that information and basically establish, hey, I see this alert. I see that it's meaningful. It's telling me that it's isolated to a particular event. Now I can go look at that maintenance action and see how it's related to that particular alert. So I'm just going to describe that in terms of what we're actually doing here and how we associate alerts to the maintenance in the system. And really what we're trying to do here is improve the quality of this set of rules, improve the ability to understand that when I get this alert, what maintenance is being performed and what should be performed, so that we can improve the overall processing of the work by the maintainer based on the alert codes that are there. So how do we associate those things together within CFRACAS? Well, it starts with the part itself. It has a particular component, has particular failure mode. What we're doing is we're saying we're going to build for that particular failure mode. We're going to build one of these processing rules. So we're going to look to the information that we have available in our alerts. We're going to tie that information together, pull it in, and use that to establish, if I have this particular alert, it means that this particular set of components have this potential failure mode. And we define those rules and build those up. And there could be hundreds of these, thousands of these rules, depending on the complexity of your system, to try and tie that all together. Then, when the aircraft flies and we're getting back the particular alerts in the system, we then look to those processing rules and we say, all right, on this particular flight, we have this particular alert code under these particular conditions. This is the processing rule that's associated with that. Here's the list of components that could have failed, and here's the failure mode associated with them. So we're basically applying that particular rule in the system. Then, as I said, what the maintainer does is he can go and look at that maintenance actions that are associated with that, because he knows the maintenance actions that resulted from the flight that just flew, because we've tied the flight to the maintenance action. And he knows the particular component that he's working on. He can then tie that back to the alert. And now we've said, here's the alert that occurred, here's the maintenance that was performed, and from there we can do in-depth analysis as to whether the alert itself was effective in identifying what the issue was, or whether there's opportunities for us to improve that alert. Vice versa, if I perform the maintenance and the next flight that I fly, I still have that alert occurring, I can establish the quality of the fix that I put in place. In other words, wasn't an effective fix. So that's really how we tie all the data together from those two different systems. And I have to say, at this point, it's still early days for us in terms of building a lot of those relationships, but we want to use a lot of AI-based technology really to tie those things together and to establish our HM data alerts giving us an accurate indication of the maintenance that should be performed, and vice versa. If we're performing the maintenance, is it helping us eliminate these issues, or for how long do those alerts disappear from the flights, and be able to establish sort of the overall effectiveness of the fix as well. So a lot of work going forward is really going to be related to how we tie these things together. Okay, a lot of details about the R&M data and the HM data and how we pull those things together, how we tie them together. The other aspects of the CFRACAS system that are important, listed here, really are what do you do about it? What steps do you take? And we have corrective actions within CFRACAS to really manage the overall process of change and improvement. And we have what's called an RSRB process that describes how we actually use that diagnostic information to affect or change the maintenance that's being performed. And I'll tackle these two things separately. So looking at the corrective actions, first of all, for those of you that saw some of the earlier presentations on FRACAS systems, a big part of what FRACAS is the ability to manage the change that goes on. And we use an 8D process inside the CFRACAS system, an 8-discipline process, which basically just walks through a formal review of the issue, identifying what the problem is, quick or triage type fixes, root cause analysis, all the way through to intermediate and long-term fixes that go into the system. So a fairly standard process. So I'm not going to go into that in too much detail, other than to say that it's available to help us manage both the R&M fixes that occur, as well as the health monitoring alert fixes. In other words, if my health monitoring alerts aren't giving me the right indication, I use this same corrective action process to improve our ability to detect and isolate faults as well. Okay, the other aspect is what's called rule sets. And the idea of rule sets really is to manage the process of making change in the field with the maintenance that needs to be performed. So let's assume for a second that we've got a working system for health monitoring data, and we have particular alerts that are occurring. When the aircraft comes back to the ground, that information is passed back to the maintainers, and they're given a list of things that they need to work on that aircraft based on the alerts that occur. That's in place today. That's a normal part of the process. But what happens when that maintenance that's defined for that particular alert or set of alerts isn't effective, isn't getting us to where we want to get to? How do they manage that change? How do they manage the process of making an update to what is expected to happen when they get those HM data alerts in? And that's what rule sets is for. It's really the idea that we have this pre-processing that goes on. We establish the alerts that occur in the field, but now we want to make a change. We're not doing the right maintenance. Perhaps we're not doing it in the right order. Perhaps we're tackling the wrong parts, and we want to make a change. We use the rule set review board inside of XFRACAS to manage that change and involve the right people to be able to make that change. And that's kind of a big part of what they're doing, is basically assessing the alert maintenance interaction findings, establishing, is my maintenance effective? Is my alert effective to identify and detect and isolate that fault, and to be able to make those changes and run that whole review process. So this is the review process that really sits around all those processing rules that we described. Now, there's some of the PMAs that we're working with that will actually take the results of this review board and incorporate it directly into their systems in the field. So they'll actually take the results of this and be able to import it directly in and actually update their maintenance management system in the field. So there's opportunities going forward for us to really streamline this whole process of review and an implementation in the field. Okay. I know we've covered a lot of ground. I know we've explained a lot of things and sort of described an overall process. Hopefully, I've kept it fairly high level and haven't lost you in terms of what it is we're trying to do. But what I wanted to do is sort of push on to the tools that we have in place inside of XFRACAS for metric analysis and what we do there. And we've actually built inside the XFRACAS tool something called the metric runner, which is a tool that basically allows us to run metrics on the data in the system using the criteria that the customer intends to focus on when they actually perform the analysis. So it's intended to be a very specific set of functions or actions that are performed inside the system. And this was a big part of what we defined when we sat down with our XFRACAS tool in the outset. We actually put together an analytical team who said, we need to create common metrics that are applied to define things like mean flight hour between failure, mean flight hour between operational mission failure, mean flight hour between abort, and a very specific definition for what those are, so that when they're reported up through NAWCAD, they always meant the same thing, no matter which program that you were looking at. So we built this out, and we actually created a standard set of metrics where we did it. We had 15 standard mean flight hour between fill in the blank type analysis. Like I said, mean flight hour between failure, operational mission failure, scheduled maintenance, unscheduled maintenance failures. All those mean flight hour between type calculations are standardized in the system. We also standardized our RAM metrics for reliability, maintainability, and operability. And we standardized our metrics for flights. How many fault detections do I get inside the system? What's my false excuse me, what is my false alarm rate inside the system? So a lot of these metrics are standardized. We also make specific metrics that really help us isolate and identify information that can be used going forward. Some of the things like fix effectiveness, a particularly challenging calculation inside the system when you have a series of aircraft and changes are made over time, sometimes over the course of years, one aircraft at a time. This fix effectiveness allows us to look at changes that occur by incrementally looking at every single aircraft and looking at how it performed before and after a fix was put in place. And we use information available on the maintenance action to actually help us with that. So again, a lot of these things are intended to streamline the work performed by the analyst in the field. Our failure suspension extraction work, particularly important for feeding Weibull and RGA analysis. We basically build up the data sets by looking specifically at the information available in the maintenance actions to gather that. And I'll tell you, that can be a real challenge when you're missing things like serial numbers and part numbers in the maintenance actions. Some of these metrics actually help isolate and identify that you have problems that you need to go correct in your data in order to be able to use it effectively. Some of the other ones in there, like high drivers list, part utilization, part performance. A lot of these are drivers that help them isolate and identify what to look at first. And we also have some other metrics in there that help us actually improve or update our systems that we put in place. We're putting in a metric now. It's not on this list, but we're putting in a metric to help us improve our overall scoring of maintenance actions for reliability, maintainability, relevancy. We've also got scoring simulators for our processing rules, so that as you add new processing rules, you can run them against existing data to determine how would things be scored with this given set of rules that I have. So a lot of different metrics are going on and being developed as part of this system. Okay, just a couple of examples because I wanted to sort of finish up with how it's actually working in practice with XFRACAS. I picked out two examples. The one is PMA 276, which is the program number for the H-1 helicopter program. The other one, PMA 262, which is an unmanned aerial system. The PMA 276 H-1 helicopter program, it's been in place for a generation. So it's in sustainment, long-standing program operated out of NAWCAD. Two different variants to the helicopter used by the Marines. They're collecting about 400,000 maintenance actions per year and about 130,000 flights. And how the system has been able to help them primarily is to allow them to do their job better and faster. They've eliminated a lot of the pre-work time associated with analyzing their data. In fact, they told us when they first put it in, they had a backlog of about 2 years of work to actually look through their maintenance actions. They were able to eliminate that in a couple of weeks using XFRACAS. So they were able to process all of their data more effectively, more completely, and in a shorter period of time, which means they can get to their analysis, their RMRB reviews. They can get to it in a timely fashion. So now they can see problems as they occur. They can be on top of things. They can fix problems and provide answers back up through the program much more quickly. And that nimbleness has basically allowed them to tackle more problems in a more timely way. And so they're a really strong advocate for the overall program and how it's helped them basically do their job. Now I'll go to the other extreme, which is the MQ-4C Triton program, which is an unmanned aerial system used for surveillance off of the deck of an aircraft carrier. It's a newer program. It's going through test evaluation right now. And what they're trying to do is understand, how that particular piece of equipment is performing. They're working very closely with the OEM now to make improvements and adjustments, and they're working continuously on the HM data that they're collecting to improve its quality and its value to isolate and identify issues. So truly the other end of the extreme. What they're doing from an R&M perspective, they're really focused on understanding how the HM data can help estimate remaining useful life. That's a big goal that they have to understand. Can I use my HM data to say how parts are failing, when I should actually be performing that replacement? And they're using this with their reliable analysis and the reliability growth of various systems on board the bird. From an HM perspective, they're heavily involved in using the tool for HM data, and we put together over 500 processing rules for them to help analyze their data. And they go through and they look at that data and they reduce it down. And really what they're trying to do is reduce it down to just a handful of maintenance actions, alerts that they need to look at any given time. Their benefits, I would say, are more expected. They're kind of earlier in the process, and a lot of the work that they're doing is very current, and a lot of the things that they're investigating are very current at this particular point in time. They're really intending to drive degrader identification, to focus on what's there in terms of both mechanical failure and in terms of bit data improvements. They really want to get to the point of establishing these rule sets, meaning that, I have these particular alerts. This is the maintenance that should be performed. They have really big plans to use XFRACAS in order to drive that overall process. And because in the unmanned aerial system, they actually have a ground station where the pilots are actually flying this aircraft. They would actually load that information directly into that ground station. And so, hey, we're getting these alerts coming off the aircraft. That means this maintenance. They get a maintenance printout sort of at the end of a flight, and that's the driving actions for the maintainers to look at the aircraft. So they can actually build these rule sets directly into their ground stations, and that's the expectation going forward. They're also a really strong proponent for sharing of data across the fleet. We're working very closely with them to get their data out there in a way that can be used in a variety of different ways and shared, and that's where pushing that data back through SDR is so important. Okay, so those are two of the examples of how the system's being used. As I've mentioned, we've implemented on 20 different platforms to date. I would say one of our biggest accomplishments in so doing was actually creating this sense of community in NAWCAD, where you had 30 separate platforms before. We now have a single team centered around the XFRACAS work that we're doing. We meet once a week. We get representation from across multiple different platforms every single week to understand, what the data is, how it's working, what changes we need to make. We've really established a very strong sense of community within NAWCAD around us, and that's really important to them going forward. It is the tool of choice now. We are actually displacing some OEM systems that have done this work in the past because now NAWCAD has their own tool. And so in a lot of ways, it's really intended to provide this common central system for managing all of their maintenance data. Just a note on where we are going forward. I'll finish with this slide. Basically, a lot of the work that we're doing is improvements to the overall process, trying to tie together this information between HM data and R&M data going forward. But we're also very, very focused on failure mode management and how to improve that side of the system. The program really is looking at relating both design failure modes that they get from the OEM to the operational failure modes that are used in the RCM world, creating a common environment for those failure modes, so that as information is being created and developed, that those two sets of users can talk to each other, the design and the operational community. And we see using CFRACAS as a participant in that process, whereas where we would track the different types of failure modes that occur. So if we get failure mode information back from the vendor, and theirs is very design centric, we could translate that immediately to operational failure modes and be able to tie that back to the maintainers and what they do. So a lot of work going on that basis to improve the overall process. So that's a little bit about CFRACAS within the NAWCAD program. Again, I hope I gave you a good sense of what it is we're trying to do there and why we're trying to do it. We've been going now for 4 years, and it's a really exciting program, and a lot of new things coming up every day. And it's something that we also apply to other programs. This is just an example. It's something we apply in other programs and other industries. And so maybe of some interest to you, the kinds of things that we're doing here. So again, thanks for your attention. Rob, I'll pass it back to you.
Excellent. Thank you very much, Kevin. That was really interesting to hear how this program has actually developed. Because I think you just said over 4 years this has been going, and I think if you go back one slide to the summary slide, it's kind of covering 20 platforms. So that is. That's a lot of aircraft types. It's a lot of, as you said, different groups that all kind of have to come together. And I like how you say that added benefit of how it's actually building the teamwork. I think that might have been one of the unexpected benefits that has come out of this. So. I think a lot of that means that there's a lot of kind of management buy-in to actually make this happen. Can you comment on sort of how that actually started? Because you need to be able to show how something could be done better. So how do you get that information across?
Right. So five years ago, great question. 5 years ago, the RCB team basically went to their management, which in this case was the Admiralty within the U.S. Navy, and said, look, we're not hitting our readiness targets because we really don't have an easy or common way of looking at these things. And so you're going to find problems here, there, and everywhere because people are running off of access databases or collecting information, and they don't really have a good sense of how to analyze it. Whereas you've got other programs which are being run primarily out of the OEMs, so the Boeings and the Northrop Grummans and whatever else, they supplied a system to us, and they have a very established way of looking at it, but it's not our own. And sometimes we have ideas within the team we want to apply. It's very difficult to do that with an OEM system. And so they came to this conclusion, and they convinced Admirals Peters and Rear Admiral Lemon that in fact this is the way forward. And so they created right from the outset the sense that we're going to go this route. Now I will say when they first did this, the focus was primarily R&M. So I showed you those two pillars, and you see them on the screen here. It was primarily the R&M. In discussing with the teams early on, we found this real opportunity on the HM side of pulling it together and putting these two things in one system. And that's been the golden nugget, so to speak, is putting these two things together. And that was kind of an unexpected benefit of the program going forward. But by creating these common working groups, as we put them together, we started them right from the beginning. We had discussions, we involved the teams. You could say we used an agile approach to our development. And in a program like this, what that means is people have ideas. We articulate that in the form of software. We show it. We work it around and around before we finally deliver it. We're working very closely with the teams all the way along throughout this process to build up the system. So that also created that sense of community and created that sense of value. And so it wasn't us coming to them and saying, hey, here's the system. It was them saying, here's the system we need, and here's how it looks. And so they owned it right from the beginning. So I think that moved it from the Admiralty, which was, here's the top down, we are going to do this, to finally, hey, this is our system. This is the way our community wants to operate, and we want to share that with the world.
Yeah, I can see how that having that ownership sort of actually makes a big difference, and also being able to actually prioritize their requirements rather than from that sort of OEM system perspective that might be for that more for a specific program. It means they can get increased commonality across platforms, I should think, as well. Yeah. I noticed one little point where you said, sort of almost in one of the examples at the end, where there was like a 2-year backlog that was sort of ingested in 2 weeks. That must sort of actually show us an example of these. This is part of the real power of the system to eliminate that.
Yeah, we built in a series of tools, and this will be important to the whole XFRACAS community. We built tools that allow us to look at maintenance actions in bulk, or incidents, as it's called in XFRACAS, in bulk. So we can change, tens of thousands of incidents simultaneously. We run a search and we say, find me all the incidents that look like this, and I want to change this property across all of them, or this set of properties across all of these ones that I just found. And you do it with a single button click. And that allows them to take systemic problems that maybe have occurred over the course of a year for a particular squadron or something, and say, hey, they've scored these wrong. And then they can adjust them all at once. So it allows them to really go through the data very, very quickly. Once they identify a problem, they're not fixing them one at a time, they're fixing them in bulk. And that was the trick to allow them to do the kinds of things they needed to do to fix their data.
Okay. Just looking at some of the questions, is this using any kind of artificial intelligence or machine learning? So sort of, is there any sort of additional kind of processing which is happening in the background?
Yeah, that's a great question. Not yet. And by not yet, that implies that it's in our plans, and it certainly is. We've been highly focused on getting the data right first before we really brought AI to bear on it. But a lot of the plans that we have going forward, one would be something as simple as saying, how can I score this maintenance action for its quality? Can I use AI tools to help me establish when I should be looking at a maintenance action and correcting the data? That's an element that we want to basically apply. So basically scoring the quality of the maintenance action itself. We also want to spend a lot of time relating the R&M and HM data together, and perform a lot of this analysis to establish the effectiveness of the HM data to understand and isolate and detect R&M work. We see AI playing a key role there. So definitely in our plans. And what you're going to see is a lot of that's going to be focused in that metrics box at the bottom, whereby you have a lot of manual or ad hoc metrics being performed today. We have plans in the next 6 months to be doing a lot more automated analysis, a lot more AI analysis through that metric runner, so that it will all happen in the background. And so we'll be pulling together that data and analyzing it in that way. And, again, sky's the limit in terms of what people want to do and what questions they want to get answered.
Yeah, but kind of the first priority is actually kind of clean and valid data, isn't it, before you start to do any machine learning or artificial intelligence? Yeah,
absolutely. Yeah, take those 4 million maps, and if I just threw 4 million maps in a system and I didn't spend the time making sure they were right and you trusted them, you would probably be garbage in, garbage out. But a big part of the system, and I sort of mentioned at the beginning, is this idea that we create the data sets, we send them back for general use. This is the only system within within NAWCAD where that data cleanup, that data correction is being applied back to the organization. A lot of other people today, if without XFRACAS, they would have to go to the originating system, which would have the original data in it. I could describe to you the challenges with that, but not having that persistent, clean, auditable, traceable data is a problem for a number of different systems today, and people look to this XFRACAS data to really help them move forward in their job.
I've just got one more question, so just looking. Are you able to talk a little bit about the kind of failure modes that are being covered by this kind of system? Because I can imagine the kind of fatigue type of failure modes and degradation failure modes, such as either corrosion or wear. But I'm imagining that this also applies to electrical systems and all other kinds of failure modes as well. Is that?
Yeah, absolutely. You know, any kind of communication system, any kind of you know, things as simple as the radio. You know, it's being applied across the radio. It's being applied across the engines and the engine components, gearboxes. Really big deal in helicopter programs is gearboxes, chipping, and things like that. You know, power degradation, that kind of thing. But it could be, you know, really any system at all. We do catapults and arresting gear, so I can, you know, we could talk at length about the catapults and arresting gear, the challenges they have with their systems and what they do, how they analyze their data, because they operate very differently to an individual aircraft, and it really is, you know, any element of the operating system in terms of, you know, failure mode. So it's mechanical failure modes, it's electrical. It's electronic, it's hydraulic, it's, you know, whatever it happens to be, whatever requires that bird to fly.
Right. Okay, thank you very much again, Kevin, for an excellent presentation. It's been really interesting. We now need to sort of move on and close, and this has been an excellent way to close our technology days this year. So we thank you very much to Kevin, and thank you very much to all our other presenters today, to Bartek and to Marius, for this introduction to FRACAS and introduction to dependability, and for Kevin for the application within NAWCAD. So excellent. So thank you very much, everyone. Thank you, and we will return and see you again next year. Thank you very much.